Hello, everyone. I think we are now online. Welcome to one more round of the ASTRAIOS webinar series. Today's webinar will count with the presentation of Dr. Marloes Penning de Vries. So the ASTRAIOS is an EU-funded project that is working on identifying the existing space-related education and training across Europe. And also the project aims to map the future demands for space skills and the space industry for the European space industry, and to identify actions to align and improve the career pathways in the sector. The project started in 2023, January, and spans over 3 years. We are now in the final phase of the project, where we are producing some education material, some courses, and so on. And this webinar is a part of that. So then this webinar is a part of the ASTRAIOS webinar series. And we hope that helps to reach the goal of improving the existing training materials and the developing of new training materials to fill the gaps between the supply and the demand for space education and training courses. So in today's webinar, we will discuss monitoring air quality from space. Thanks again for our guest, Marloes Penning de Vries. She's here on my side, that's why I'm looking sideways. Dr. Marloes is an assistant professor in the Department of Natural Resources, right? Water Resources at the University of Twente, at ITC, in the Faculty of Geoinformation Science and Earth Observation. And now I'll give the floor to Marloes to talk a little bit more about this exciting topic. Thank you again, Marloes.
Thanks a lot, Ryan, for the introduction, and of course for inviting me to give a lecture about monitoring air quality from space. What you see here on my very first slide is an artist's impression of the Dropomi instrument, and this is an instrument that sort of revolutionized the monitoring of air quality from space, and I'll be talking quite a lot about it. But you'll see that a lot of other satellites and instruments feature in this talk as well. But let me start off. If my system allows. Yes, by introducing myself, because I think it's good to know who's speaking here. My name is Marloes Penning de Vries. Ryan already said it. I'm actually a chemist by training, because I did a bachelor's and master's degree of molecular sciences at Wageningen University. Then I turned to spectroscopy, or specialized to spectroscopy, while doing my PhD in Frankfurt, working on protein spectroscopy. And then I found that my interests were more towards the sky than towards the ground. So I moved to atmospheric chemistry and became a remote sensing scientist during a long-term postdoc at Max Planck Institute for Chemistry, which is in Germany, in Mainz. And followed by that, I worked on the water cycle, also using satellite instruments at the German Weather Service. And after that, I moved back to the Netherlands, where I'm originally from, and became assistant professor of water, air, climate, and health interactions at this ITC faculty at University of Twente. This is not me, however, in the picture. So what I'd like to do is first, before I start talking about air pollution, I would like to know what you know about air pollution. So I'd like to invite you to a quick quiz in WooClap. So please go ahead and enter into this WooClap. I hope you know how it works, but I think you'll find out if you follow the QR code or go to wooclap.com and enter this event code. I'm not sure how to do this, because now I think
you just type wooclap.com / the.
Yeah, but I have it open, but I have to move towards it. like this, so it's still there. I see some of you have already joined. I'll just wait a few minutes. The quiz is totally anonymous. It's just to get an idea of your thoughts on air quality. Thanks for the thumbs up. Let me get started, and then I hope others might join later, because the event code is always at the top of the screen, so you can follow it. The first question is, do you believe it's true or false that air pollution leads to reduced lung function, asthma, and COPD, which is constricted, I don't remember the exact acronym, I'm sorry, but this is also a lung disease. Just waiting for everyone to answer before I show the result, so that you don't you're not influenced by each other. Okay, we've got almost all results in. All of you think this is true. Then let's go to the next statement. I'll give you the answers later. This is just that this is a poll of what you think. Air pollution is the second highest risk factor for non-communicable diseases. Means diseases that cannot be transferred from person to person. Don't look up the answers on the internet, eh? That would be cheating. So most of you think this is true, and we've got 2 persons answering false. I'll move to the next one. Air pollution is associated with impaired cognitive functioning and increased risk of dementia. You're very quick in answering. So all of you think this is true as well. Let's see how that is with the next statement. Ambient outdoor air pollution in cities and rural areas caused about 4.2 million premature deaths, and that should read in 2019. This is the question doesn't fit on the screen. So about 4.2 million premature deaths. Okay, thank you. So 2/3 think this is true, and 1/3 thinks this is a false statement. 2 more coming up. So of these premature deaths, about 89% occurred in low and middle income countries. Is this true or is this false? So about 89, so let's say 90% of the 4.2 million deaths due to outdoor air pollution. Okay, most of you think this is true. Then the final one, now this is one you have to guess. What percentage of the world population lived in places where the WHO air quality guidelines were not met? This is in 2019. just a rough estimate. What percentage do you believe live in places where the air quality guidelines were not met? Let's see what statistics you have. So something between 70, 75, 80, 62. That's a very accurate guess. And 85%. So I'll get back to that in a second. Thanks for answering those questions. I have one final one, but this is more about how you feel about air pollution. So how do you rate the air quality at your present location? Is it perfect? Is it sort of good, acceptable, bad, terrible, or do you have no idea what I'm talking about? Which is also fine, by the way. Thanks for voting. Ryan, what do you think of the air quality in Enschede today?
I think it's quite good, at least compared to what was used to in some cities in Brazil. That's, of course, I'm from the countryside there, which is quite good there as well, but big cities no.
Big city, no. Okay, let's see. Okay, I'm very, very happy to see that a lot of people live in or are in places where the air quality is good right now. But I see also some participants in places where they feel the air quality is bad. Thanks a lot for answering those questions. Let me continue with my presentation, if I can find it. Oh no, sorry. It's this one. Because I'd like to tell you that the World Health Organization, WHO, really cares about air quality. Because all the statements that I showed you were true, and air pollution is, in fact, one of the greatest environmental risks to child health. And then these are all statistics from 2019, but then 99% of the world's population was actually living in places where the WHO air quality guideline levels were not met. So this even exceeds all of your estimates. I saw 85 was the highest, but it's actually 99%. So there's hardly any people living in places where the air quality guidelines are met. That's rather worrying, but there's also things that we can do, because it has been shown that policies and investments that support cleaner transport, energy efficient homes, power generation, industry, and better municipal waste management would reduce key sources of outdoor air pollution. And at the same time, because many of the sources of air pollution are similar to greenhouse gas sources, this would also mitigate climate change at the same time. So this is something to act upon. Now, that was just sort of an introduction. What I'm going to talk about today is, I'm going to talk about monitoring air quality from space. And what I'd like to start out with is setting a framework. So what is air quality? What is air pollution? What are the sources and what are health effects? Then I'll go into air quality monitoring. Why do we want to do that? But also how? And I'll show you some applications of satellite-based air quality observations, because that's my focus, the satellite observations. And I'll demonstrate how you can get your own maps of air quality information, both from the Sentinel-5P mapping portal and from the Giovanni platform. So this session, I hope, will enable you to argue why air quality monitoring is necessary, but also describe how air quality is monitored from the ground and from the sky. Explain how satellites, models, and monitoring stations are complementary, so we need all of them. I'll explain why. And then I'll show you how to explore freely available air quality data from a couple of platforms. So the first question is, what are we talking about? What is air quality? That means we first have to talk about what is actually air. Well, let me tell you that 99.99% of the air is actually clean. as you'll see in the blocks shown on the right. Most of our air, as I think most of you will know, is nitrogen, which doesn't react very much, doesn't do very much. 20% is oxygen, which is extremely important and does a lot. There's also a bit of argon. We don't really care about that because it's also quite inactive. And then there's CO2, which makes up about 0.004% of our atmosphere and is increasing, as you'll know. And the rest, I don't know if you can see it on your screen, but there's a tiny green cube, which is the rest, the other stuff in the atmosphere. This is the dry atmosphere, so there's also water vapor as well, which we can consider clean. So what is this rest? These are gases, for example, nitrogen dioxide, you might have heard of that, ozone, also organics, both from biogenic sources, so from trees, vegetation, but also anthropogenic, so from humans, and inorganics. Essentially, everything you can smell is part of that rest. Then there's large particles like pollen and plastics, microplastics, or coarse dust and things like that. And we have small particles, fine dust, smog as well, and smoke. And sometimes these are measured in PM 2.5 and PM 10. This might be familiar. So where does all this stuff come from? Well, they're natural and anthropogenic sources, like I just said. What you see in this image are on the left are mostly the natural sources. So there's volcanoes and wildfires. This is an American picture, so they didn't put dust there, but in many regions of the world, dust is a very important natural pollutant. Then there's the anthropogenic sources, and these can be, well, they're mostly from industry, but also from traffic, from agriculture. That's sort of depicted in this picture. And I think what has been sort of the approach of people, of civilizations for the past 100, 200, or even more years, is that if you throw something away, it's gone. So you see these the stacks on the factory. You blow things up high into the air, and then it's just gone. But actually, up is not away, as you'll see in this next schematic, because you see that what goes up comes down as well. So we generate emissions, or they come from fires or other natural sources. They go up into the air, and then they come down somewhere. Sometimes that's in a remote place, which is sort of what you might favor because it doesn't affect you. But sometimes that's also on within a city or other places where people live. I'll not go into the biological effects that these depositions have, but of course that's also something that is a consequence of transport of pollution. And now you see on the right figure, it says transport and chemical reactions, because the atmosphere is not inert, so things are going on. The gases react together. This is why we divide air pollutants into primary and secondary air pollutants. So primary pollutants are gases and particles which are emitted directly into the atmosphere. You see those in the left and listed in the left cloud, things like carbon monoxide, which comes from fires or incomplete combustion. Also sulfur dioxide or nitrogen oxides. And in the atmosphere, these pollutants can react with physical chemical reactions and become secondary pollutants. So they form something different. You see a list of those, for example, ozone, but also sulfuric acid. This is something you might know as acid rain. So they can also form particles and all kinds of other processes. So that means that both meteorology, so temperature, humidity, and all kinds of profiles of the atmosphere, as well as the composition of the atmosphere itself, influence the concentrations and the profile of these concentrations in the atmosphere. And that's something that makes our measurements actually pretty complicated. I'd like to go a little bit into the particles. This is actually what I work most with. Particles are sometimes by remote sensing scientists called aerosols, which is confusing, but I'll probably use them both, so pardon me for that. These are small particles that are suspended in the atmosphere, and I made a sort of a schematic on the right. They scatter and absorb radiation. They stay in the atmosphere for anything between hours, days, and months. And we can similarly separate these into primary and secondary aerosols. Now, the secondary aerosols are those that form from gases in the atmosphere. They're small, so between 100 and 500 nanometers, and round droplets generally. And some examples, some well-known examples are smog, which you see depicted in the photograph. Also fog, which is volcanic smog, actually coming from volcanoes, and biogenic aerosols. Primary particles or primary aerosols, on the other hand, are directly emitted. They're mostly from natural sources, and they're medium to large size, and they come in various shapes, which is sort of depicted in the schematic on the right. Some examples are smoke, which we can, well, it's not always a natural source, but also dust storms and volcanic eruptions. They create primary aerosols. So what do these aerosols, or what does this air pollution do to our health? We talked a little bit about it in the beginning. I'm sorry for this graphic. It's labeled in Dutch, but I think it's one of the best graphics that I've seen for this. You might recognize the organs that are affected. We know that nitrogen dioxide and ozone cause coughing and shortness of breath. You might know this from if you go out in a smog. But on the long term, this also affects lung function. It can cause asthma, particularly in children, and COPD. And then we have the particles, which I just talked about. They can penetrate into the lungs, and the smaller the particle, the deeper they can go into the lungs or into the blood system. They can lead to heart disease, strokes, and cancer. But they also been shown to affect cognitive development, even in immediate cognitive functioning, and induce dementia. So these are things that we should really take seriously, and most at risk are the children, elderly, people with pre-existing conditions, also pregnant women, and people in economically disadvantaged regions. Now, on top of that, we know we live in an era of extreme climate change, and heat stress exacerbates the effects of air pollution, which means that we're probably looking at a problem that's becoming even bigger with time in many regions. This is why the WHO, so the World Health Organization, introduced some standards. This is a slide that I borrowed from Maya Sundström from FMI. So the World Health Organization has suggested some standards, which you see all the way on the right in the table, AQG and level. These are the newest standards that they have suggested. These are not legally binding guidelines, but they're used as standards in air quality legislation. So countries tend to try to stay below these levels. You can see that there are two different values. I'm not sure if you can see the pointer, but so there's a value for annual average guidelines, which is much lower than for the 24-hour average, because there can be peaks which are acceptable, but on the long term, you would want the air quality level to be below the ones given for the annual average. So why do we then need to monitor the air quality? Because, I mean, there's nothing much you can do about it if you're in a situation like the one depicted on this photograph. We know that in many countries there are air quality regulations, but they cannot be enforced because there's a lack of monitoring capabilities. So we need data with which we can, well, first of all, create forecasts and real-time warnings so that you can warn the public not to go outside or not to do too many sports activities or things like that. Of course, we can also perform research to better understand what's going on, for example, in the atmosphere, what kind of reactions are going on, and how can we prevent these if required. We can also use to identify pollution hotspots so that governments can take action. And we can evaluate control measures that are then put in place. So that's the why, but now we come to the how. How do we do this air quality monitoring? Well, let's say we have a monitoring station, which is depicted here schematically in black, and the pollution is given in these gray dots. In this case, the pollution is very close to the ground. So the monitoring station measures at what we call nose level, which is the level that's relevant to human beings. We usually measure in mass concentration, so micrograms per cubic meter, for example. These are point measurements, so they're representative for a very small area. You can also do airborne or satellite-borne measurements. But in this case, as you see, the instrument is very high above this layer, and it detects all of the atmosphere that's beneath it, and often also that, well, in two ways. This is what for aerosols, so for particles, we call this the aerosol optical depth. You can also have the gas optical depth. It means we're only measuring the effects that the gases or particles have on sunlight. We do not measure the particles directly. It's an indirect measurement, which means that we also need to do assumptions and some calculations. Now, these measurements are in general on a much larger scale, particularly the satellite measurements. So to go a little bit into more detail, this is a monitoring station for air quality in the Netherlands. So there are research institutes. Well, in the Netherlands, this is TNO, who do air quality measurements with very well calibrated instruments. But these are actually quite expensive, so you can only do few stations per region. While a wealthy country like the Netherlands still has quite a lot of these stations, but still you can see that particular regions, and in fact the region where we are staying in Enschede, is not well covered with these instruments. What you can do is you can also install low-cost air quality sensors, and there are a lot of citizens that are interested in doing this. So a low-cost air quality sensor can cost around 100 euros or dollars or something like that. They are not as well calibrated, of course, as this big TNO bus, but they are a large number, as you can see on the right, which means that you also have some sort of a truth in numbers, and they can help increase the coverage of such a network. These are some examples of air quality platforms that collect data from all kinds of citizen sensors, so these low-cost air quality monitors. And you see that there are actually worldwide, there are quite a large number of these sensors, and often people connect them to the internet so that they don't only measure their own air quality, but can also share that with the world. These are, for examples, Purple Air, World Air Quality Index, IQ Air, and OpenIQ. But on a second glance, I think you notice something about these maps, and that is that Africa and other parts of the global south are actually not well sampled. You see very large areas in South America, but also in Asia, and particularly Africa, that have no air quality monitors. So what we can then do is monitor air quality from satellite, because there are a lot of dedicated instruments that do air quality observations. For example, TROP-OMI on Sentinel-5P, and there's an image, another artist's impression of what TROP-OMI measures on the lower right. Satellite instruments make regular and consistent measurements over a long time range. They have a large coverage, and they also detect remote regions. This is an example from the Sentinel-5P, so TROP-OMI instrument, where you can see the region where we are residing now in the Netherlands, that there's quite a lot of NO2 pollution, and we'll go into that later. Satellites also have a disadvantage. They have a low spatial resolution, tens of square kilometers, which is almost sufficient. Well, it's, as you can see on the image on the upper right, you can separate cities, but not streets, let's say. Moreover, they have a low frequency of measurements. So this is once a day and only in daylight. And as I mentioned before, this is an indirect measurement of the whole atmosphere, so not the concentration at nose level that you were actually interested in. But recently I've had to revise this slide because the low frequency, the 1 times per day, has changed since the launch of new instruments, what you see here. So nowadays there are also geostationary air quality observations. The TEMPO satellite, now I have to start with GEM satellite, which you see on the right, has been doing air quality measurements over Southeast Asia for the past 2 or 3 years. TEMPO has also recently started collecting data over the continental United States. And Sentinel-4 has, I think, just reached its geostationary orbit. It was launched a month ago and will cover Europe. So you see that the constellation of geostationary satellites will deliver sub-hourly air quality data for large parts of the world, but unfortunately not all. Now, to give you an example of this air quality monitoring for satellites, here you see a map of NO2, nitrogen dioxide, which is a pollutant that very clearly shows up in the source regions. This is one of the first pictures that came out of the Drop-Only mission, which started in 2018. And you can recognize the patterns. In the Netherlands, there's a lot of pollution as well as in England, the Po Valley region, and we see dots where the large cities are located or where large industrial centers are. What you can do with these regular measurements is you can do comparisons. So what you see here is a time series over China in February 2019, 2020, and 2021. I will all remember that was the time of the COVID lockdown. And what you can see is then that in February 2020, the concentrations of nitrogen dioxide over China were significantly lower than in 2019 or 2021. Now, there's one more topic that I'd like to touch upon regarding monitoring air quality, and that's using models. Now, there's many different models. They're based on some combination of physics, chemistry, also statistics and other mathematical equations. Often they use observations as well, and they make use of databases, for example, of emissions of gases, but also land use and all kinds of other databases. Now, the nice thing about models is they provide information without gaps. So the satellite data, you also always see gaps because the instrument maybe was not functioning, or because there were clouds, or for other reasons the inversion didn't work. But models always provide information. They provide it on different spatial and temporal scales. You can even look at different layers in the atmosphere. You have many different variables, which can be used for different purposes, of course, and also different models can be used for different purposes. So in this case, this is the Lotus Eurus model. It's an air quality model developed in the Netherlands. And you see that we can, well, I showed the NO2 map, but we also have ozone. You can look at the particulate matter, small fine particles or the coarse particles. You can all get this information from one single model run. Now, I'd like to show you another model, because the nice thing is that you can also distinguish between different particles. So let me just start. Oh, did that? I hope this works with the...
What if the sky held secrets you couldn't see with the naked eye? In this breathtaking NASA visualization, the atmosphere comes alive with color, revealing a hidden world of aerosols, tiny particles that travel thousands of miles through the air, shaping weather, climate, and even our health. These aerosols come from both natural and human sources. You are looking at sea salt in cyan, whipped up by powerful ocean winds. Dust appears in magenta, lifted from the vast Sahara Desert and blown across the Atlantic to fertilize the Amazon rainforest. Black carbon, a byproduct of wildfires and the burning of fossil fuels, glows in fiery orange and red, and sulfates, shown in green, stem from volcanic eruptions and industrial emissions. Zoom into South America, and you'll see smoke, black carbon, billowing from fires in the Amazon. Off the coast of West Africa, massive dust clouds drift westward, eventually reaching the Americas. These invisible travelers don't just affect air quality, they influence cloud formation, weather systems, and even the global climate. This visualization is powered by NASA's Goddard Earth Observing System model, a cutting-edge system that fuses satellite data, ground-based observations, and complex atmospheric modeling. GEOS gives scientists an unprecedented view of how aerosols evolve, where they go, and how they interact with the planet. By tracking these particles in real time, researchers are improving air quality forecasts, refining climate models, and advancing AI-driven prediction tools that may one day help us better protect both people and the planet. If you enjoyed this journey into Earth's hidden atmosphere, there's more where that came from. From Mars to magnetars and everything in between, we explore the universe one discovery at a time. Subscribe to Beyond Earth, buckle up.
So that's the power of models, that we can we can even see which type of aerosols or particles are going in which direction. That was essentially it for the theory that I wanted to share with you. I'd like to go into a few applications now of satellite data. I'll first show you a little bit about NO2 air pollution and ship tracks. Then I'll talk about methane and particulate air pollution. So I've shown you this figure before. I'd like to go in a little bit more detail. So nitrogen oxides form during high temperature combustion. And NO2 is actually very well observable by satellite because it has a very typical signature in this in the visible wavelength range. The natural sources are limited, which means that what we see is mostly close to the ground, or is anthropogenic, and it's a short-lived trace gas, which means it decays very quickly, and so that we can only see it very close to the sources. And that's the combination of these things is that we really see the sources very well. We can really see all the European capitals on this figure. And there's something else that you can see. I don't know if you've detected it, but if you look closely, you see some strange lines going on here. I'll give you a second or so to think about what this could be. These are actually shipping emissions. So you see that over ocean, there are very few sources of NO2, so we can see these small enhancements even from space. And this is a picture of individual ships that move along. This actually from 2012, but the shipping lanes haven't changed that much in this region. So you see that there are particular shipping lanes where most ships pass by, and you can see those very well in the NO2 map as well. Now, the Sentinel-5 isotrope-OMI instrument is really an unprecedented instrument that has a very high signal-to-noise ratio. It's an excellent instrument, and this could be used to detect individual ships. So what you can see on the image here is one trope-OMI image. You can see these colored dots. These are all single measurements of trope-OMI of NO2. With reds indicating higher values and blues and whites lesser values. And these purple dots, this is the trajectory of the ship. So there was a ship that was here at the time of the overpass of the instrument, and it came from here. Now, why did trope-OMI detect the NO2 a little bit lower? This is because of the wind speed, which you see in these arrows, the wind speed and direction. You see that the older emissions were blown a little bit more to the southeast. And this they could detect from this is just from a single ship. And if you then look at, this is a whole shipping lane, you see a lot of these different ships. It's a very confusing picture, but you see many different ships there. You can use that and quantify the concentration of NO2. And if you do some magic tricks, you can even quantify the emissions. So you see here, given in black, this is the NO2 concentration that was measured for the ships. These are all different ships that they identified. And you can invert that and then calculate the emissions from each of these ships. And that's very helpful because in this way we can aid the enforcement of regulations of shipping emissions, because it's very difficult to measure the emission of a ship that's not in a harbor. There's another thing that's nice to study about the NO2, because we know that pollutants have different patterns, for example, seasonal patterns due to emission patterns, or but these can also be due to meteorology. You can have diurnal patterns, which also can have to do with meteorology, but weekly patterns are really very typical for humans. There's no natural process I know of that has a weekly cycle. So if you detect a weekly cycle in a pollutant, then you're pretty sure that this is mostly human. And that's shown here in a study that was already published in 2003 with a satellite with a very coarse resolution. But we can already see that here in Europe, on a weekday, the NO2 values were much, much higher than on Sundays. In that study, they looked at different regions of the world, different cities, and I don't want to go into too much detail, but you see that in the United States and in Europe, there was a very clear minimum on Sunday of nitrogen dioxide, whereas in the Middle East, there was a minimum on Friday, except for Jerusalem, which had a minimum on Saturday, which all fits with their respective days of rest. And at that time, they were unable to detect any minimum in China. This study was done again later in 2020 with a better instrument, with Tropomi. And what you see here is depicted in dots cities that have a particular day of rest, so a particular minimum in NO2 concentrations. And you see that most of the world rests on Sunday. In the Middle East and Islamic regions, there's a Friday rest, and then there's some Saturdays that might or might not be might not be attributes, but that also show up on this map. So this is a very nice way of separating anthropogenic from natural sources. Now I'd like to make a little excursion, because methane is not directly linked to air quality. Methane is not something that we generally have health problems with, but it is a very potent greenhouse gas, and it comes from often from oil spills or from gas leaks, but also from waste dumps. So what I would like to show here is that you can also combine different satellite instruments so that you can complement the spatial resolution of one with more frequent measurements. So in this approach, there's a combination of Tropomi, so Sentinel-5P, which detects the methane. Then there's an instrument on Sentinel-3, which is called SLSTR. It can quantify the amount of methane. It has a much higher resolution than Tropomi, you see. And then you can use an instrument on Sentinel-2, MSI, which has an even higher resolution. It's not so good at quantifying, but it's very good at pinpointing the location. So you can really use these three instruments together to find where the methane leak is and quantify how much methane is coming out. And this is really being used operationally to get industrial companies to close their methane leaks. The final application that I'd like to talk about is the particles, so the aerosols. And I'd like to go one step back. So you've seen this picture before. I talked about you can quantify aerosols as number concentration, so the number of particles or mass per cubic centimeter or per cubic meter. If we do a satellite measurement, we use aerosol optical depth or aerosol optical thickness sometimes, or the visibility. Now, this optical depth is a parameter which quantifies the extinction of radiation. So how much interaction was there between the particles and radiation? You can do this also from the surface using a sun photometer, which you see in the figure on the right. This is part of the aerosol robotic network. I don't want to go too much into this equation. It's actually relatively simple way of comparing the measured radiance with the radiance that you would expect to come from the sun, and then you can calculate sort of how much radiation has disappeared from your measurement. What you then can obtain is a time series as shown on the left for different wavelengths. Now I won't go into detail there, but this is something you can compare very well to satellite measurements. Now, just to make that a little bit more tangible, these are measurements over a station in Morocco. And on the first day, on 15th of April 2023, this was a very clear day. We see that in the values of the aerosol optical depth measured by the sun photometer. We also see it on the right. It's a very, very clear satellite image. Whereas on April 7, this was quite hazy, and you can see that the image is much more murky, sort of milky. This is what the satellite sees and then has to try to interpret. So this is actually what makes it difficult. We measure an AOD from satellite, so the aerosol optical depth. This is a total column, which means the aerosols might be near the surface, but they might be higher up. And it also represents a spatial average. There's a contribution from all kinds of particle sizes, and there might be all kinds of meteorological factors acting in here. On the other hand, if you have the measurement at the surface, well, that's what we're interested in, the nose level concentration, but it's a point measurement. So if you compare that, this would be a satellite pixel, and this is the point measurement. Often there's a limit for specific sizes. For example, PM2.5 only detects aerosols or particles that have a diameter smaller than 2.5 microns. Well, similar to what we see in the AOD, the concentration can be affected by meteorological factors. So we know that there is a relationship between AOD, so what the satellite measures, and ground-based particulate matter. You can see that in this example for AOD measured over Kigali. This is on the top graph, you see the AOD, and in the lower graph, you see the PM2.5, so the particulate matter measured at the US Embassy. You see that there's a very similar time series, but they're not the same. So when we want to estimate the PM level from satellite, you need to find out what this relationship is exactly. There are many different ways to do this. You can use statistics, for example, using a collocated data set. You can do different linear methods or multivariable methods. We can also use machine learning, and this is being used more and more in the last few years. Yeah. Then do I still have some time? Mm-hmm. Okay, then I'd like to do some more. I'd like to just show you about where to find satellite data and how you can make maps of those yourself. So I'd like to start off with an example from the Sentinel-5P mapping portal about volcanic SO2. And I'll have to find where I put that one here. So you'll find the link in the presentation to this mapping portal. This is funded by ESA and by the European Commission. And if you go to this portal, you'll see a standard map of NO2. This is for the most recent time period that's available. But now I don't want to look at NO2. I would like to look at SO2, which is a volcanic product. Currently, Etna is apparently is erupting, so we see some SO2 there. But where I actually wanted to go is somewhere else, because there's quite a big eruption going on here. Now I'm not quite sure of the name of the volcano, but we see quite a lot of SO2 coming out of a volcano here on the eastern edge of the DRC. And what I can now do is I can make a side-by-side comparison. So if we look at yesterday, the day before yesterday, we can slide over and compare and see actually where this cloud of SO2 was moving. So the day before yesterday it was here, and now it's moving over to Rwanda. And we can have a look at what happened the day before that. It was moving more to the north. These data sets can also be downloaded. I will not do that right now because it's quite a large data set. But if you'd like to have a map like this, you can just simply download it to your computer and work with it. Now, the other platform I'd like to show you is Giovanni. That's this one. It's created by NASA, and this contains a very large number of data sets. So the first thing you'll have to know is what you would like to look at. You can select different disciplines. Well, if I would only look at particles, aerosols, you see there's already 274 different data sets. But we can, what I did is I already selected a particular instrument that I would like to use, which is the MODIS instrument. And I've selected a data set here. This is an AOD, you see, aerosol optical depth. And it's a mean, daily mean at 1 degree spatial resolution. Now, I selected a certain type of a plot. I can make a time average map for a certain region. I've selected the month of August, so the most recent days. So that's the 8th of August until the 17th. You see, it's not the newest day. And I selected the region over over the DRC because I wanted to look at what happened with the volcano. And what you see here is I've saved these data because it takes some time to plot, but this is what you obtain. So this is a time average map. You see this is a very low aerosol optical depth, and it goes up to 1. We see a very big cloud of aerosols, so particles, over the DRC. And remember that here was a volcanic eruption. Now I can tell you that this doesn't come from the volcano, and we'll look into that in a second because I think I still have some time to do that. But before we do, I'd like to show one other option that's possible. I'll go back to my data selection, and instead of a time average map, there are other plots that I can make. For example, I can make a time series. That's also something that I did already for the same data set. And you can see that here, this is the plot. Now you see there's a time series for the map that I showed you before. It was averaged, and then you can just get this time series. You can download the figure or you can download the data. And you can see that there was quite a lot of aerosols for all of August, and there's a big peak coming up. Now, where does that come from? There's one final thing that I'd like to show you. And this is actually the ground-based air quality models. This is IQ Air. And we're now in the region where we were looking. So maybe I should make it a little bit. Don't know if that's going to work. I'm going to zoom out a little bit. What you see here is a map with different air quality monitoring values. So from stations, but they also made an interpolation using other data sets. And you see that there's quite a high amount of aerosols, so particles over DRC. And now we also see the reason, because there are fires detected, and these are mostly caused by fires, the air quality. We can select stations here to see what the quality is. Well, this one is quite a bad air quality, as you can see, almost 60 micrograms per cubic meter. We see something of a history. Some of the platforms have longer archives than others. This one has only 24 hours. So that was actually what I wanted to tell you today. I've collected some of the links that I've been showing you. So the Sentinel-5, the mapping platform, Giovanni, and the IQ-Air were what I showed you before. There's also the Aeronet, Sun Photometer Network, and I listed some other AQ air quality platforms as well. And finally, I have some literature references for you that show where I got the figures that I showed within this webinar. So thanks a lot for your attention, and I'll be happy to take some questions.
Okay, thanks a lot, Marloes. It was great to count on your presentation. It was quite interesting, and we have quite some questions here in the chat. Just one note, when asking the questions, since this recording goes to YouTube later, I don't tell the name of the person because of the privacy protection. So that's why I will not read the names of who asked the questions. So the first one is very interesting, that is more on the skills related for working with that. So the person asked, what are some hard skills required in air quality monitoring and improving?
That's a very good question. Thank you for that. This is going to be a very scientific answer. It depends. I think it's always very good to have a basic knowledge of what you're looking at, which is why I started out with what is in the air and how can we see it. So if you want to work with satellite measurements, you have to understand something about what the satellite actually sees, because like I mentioned, it's not that it counts particles. It makes a lot of assumptions, and you need to know under which conditions these assumptions are valid and when they're not. So if you really want to do some analysis with satellites, then you should know a little bit about how those work. Nevertheless, there are also a lot of data sets that already did a lot of this stuff for you, so particularly from NASA or from ESA, and you can get to work. In any case, it's always useful to know a little bit of programming, because generally what you can download is not what you need. So you still want to do, this, Ryan. So you generally need to do a little bit of programming to make the right average or to make just the image you want. I hope that's helpful.
That's great. Yeah, thank you very much. Another here more related to the data itself. You showed 3 satellites which monitor air quality in specific areas of the world. Who are they led by? Is it an international organization or regional ones? As I noticed that there isn't any Russia and East Asia data.
Yeah, that's also an excellent question. Thank you. So the 3 instruments that I showed that you're referring to are the 3 geostationary ones. And indeed, the one is led by Korea. The finger one is China. We have the Americans, of course, and the Europeans. There are a lot of satellites, as you know, and many of them are launched by commercial companies, but these always look only at RGB images, so looking at structures or things like that. These have commercial interests, but air quality is not something that is done by commercial companies, and so it's the big space agencies who do that. So that would be the ones I mentioned. So that's the Japanese space agency, but also the Chinese and the Korean. And then on the other hand, it's the European Space Agency and it's the NASA. I do not know of any initiatives by other space agencies for doing air quality measurements. So the countries that are not covered by the 3 geostationary instruments will still have to make do with the polar orbiting ones, which cover all of the Earth, but only once a day.
That's great. Thanks. I'll combine now 2 questions, since we passed a little bit the time, was just to finalize. That is, besides the monitoring capability, how can we contribute for improving air quality? Like how this quality monitoring results, and how that can be taken by public policies to help on decreasing the air pollution and mitigate the climate change. And if there is any case of success that that of regions that managed to decrease that.
Yeah, another excellent question and on totally different perspective. Thank you. Well, the first thing is actually awareness, because a lot of pollution is actually created by, ourselves, by people. This industry is one thing, but just by driving vehicles and heating, for example, this causes a lot of pollution. In the Netherlands, one very clear example is using wood stoves to burn. It's nice to sit in the garden and have a wood stove on, but this creates a lot of pollution actually that may bother your neighbors, probably not yourself. This is really one of the biggest sources of pollution currently in the Netherlands. So that's one thing. Awareness raising is a very, very important one, because pollution is, I think I wrote it in my abstract, it's nicknamed the silent killer. So a lot of people are not aware of how bad it actually is, that pollution is really killing a lot of people. That's the one side. The other side is, it's doing these measurements, even if you have your own instruments. It also contributes to awareness, so then we can see where the problems are, where the sources are, and get policymakers to do something about it if it's not in our own hands anymore. But I do see that it's really important, first of all, for human health, but also, as was mentioned also even in the question, to mitigate climate change, because a lot of the sources are the same. So if you then reduce pollution, you also reduce the greenhouse gas emissions.
That's great. Thanks, Marloes. I think I'll go for one last question only, and then we can close it. So this I also combine two. First, how do the satellite measurements correlate with the ground sensors? And if you have explored machine learning for this combination of between to correlate and combine the ground sensors and the satellite measurements.
Yeah, exactly. There you point to something that's really a current development. So I only touched shortly upon the fact that relating the satellite measurements to what's actually going on the ground is difficult, because if we look at the gases, NO2, for example, is emitted close to the ground, and something happens in the atmosphere. So the concentration is not the same over the whole atmosphere, but the satellite sees the whole atmosphere. So you have to somehow compensate for that. But that's even more the case for these particles, because there are many different types of particles, different sizes, and they have different effects on radiation. So satellites cannot always distinguish between those. There are different ways to approach that. You can either use machine learning methods to learn, but then you need the truth, right? You need something to train the data on. You can do that. In some cases, it's even a linear relationship between AOD and particulate matter is acceptable if you have very only one particular type of aerosols, for example, that's being emitted. This can also work. That's a first approach. Another approach is using these models that I showed, like air quality models, which explicitly include the emissions and also interactions within the atmosphere. That's also a way to close the gap. But they all depend on the input of measurements as well, because these emissions are never complete. Let's say the input is never perfect. So this is why I was saying you really need the combination of the satellite, also the ground-based measurements, and the models. We need them all.
That's great. So we come then to the end. Thank you very much, Marloes. I'll just share now some last information about our project. We have here the information about our web pages. We have here our website, our LinkedIn, our X page as well, and our YouTube channel. This webinar will be posted, the recording, in the YouTube channel later. So if you want to share with people that could not watch it, you can share with them the link later. All the other webinars are there also in our YouTube channel. So thank you very much for everyone, and I hope to see you in the next webinar. Thanks a lot, and bye-bye.
Thanks, bye.